Thank you very much. So thank you very much for the invitation. This talk is based on a joint work with Serban, and more precisely on a new version that will be posted soon on arXiv. It's well known now that random matrix theory and operator algebra theory have fruitful interactions, and the aim of this talk, this work, was to solve the so-called Peterson-Thom conjecture via a random matrix conjecture of Ben Ice, as mentioned by March in his talk on Monday. And first of all, let me very briefly remind you of the so-called G.U.E matrix. It is a n by n self-adjoint random matrix with entries on the diagonal and the real part and the imaginary part of the entries above the diagonal multiplied by square root of 2 are independent standard Gaussian random variables. By standard, we mean zero mean and variance 1. And we normalize this G.U.E matrix by square root of its dimension in order to have this convergence result, namely the so-called Wigner's theorem, stating that the empirical spectral measure of the rescaled G.U.E matrix weakly converges towards the semicircular distribution. And this histogram of a 1000 by 1000, the histogram of the eigenvalues of a 1000 by 1000 G.U.E matrix illustrates this convergence. But actually, one can formulate this Wigner's theorem in a more algebraic way by introducing so-called standard semicircular non-commutative random variable, which is a self-adjoint operator in a C-star non-commutative probability space A phi, whose moments coincide with the moments of the semicircular distribution, so that we reformulate the Wigner's theorem by saying that the moments of the rescaled G.U.E matrix with respect to the normalized trace converges towards the moments of the semicircular non-commutative random variable. And thanks to Dan Wojciechowski's result, this can be extended to several independent G.U.E matrices. For this, let us introduce a standard free semicircular system, which is just a R tuple of standard semicircular operators, which are free according to the definition of Dan Wojciechowski. And in the 90s, Dan Wojciechowski realized that a tuple of independent normalized G.U.E matrices provide asymptotically a model for free semicircular systems, since the normalized trace of any polynomial in independent G.U.E matrices converges towards phi of the same polynomial evaluated at the semicircular system. And later, Hagerup and Tjobersen proved that actually this convergence holds in norm. And this is called strong asymptotic freeness. And these results had numerous consequences for operator algebra issues. But this conjecture, called Peterson-Thom conjecture, was still open. And I won't go into the details of this conjecture since it's not at all my field of expertise. Fortunately for me, Ben Ice formulate a random matrix conjecture, which he proved that if this random matrix conjecture is true, then the Peterson-Thom conjecture will be true too. So let us look at this conjecture of Ben. assume that you have a tuple of R1 G.U.E independent matrices and another tuple, an independent tuple of independent normalized G.U.E matrices, Yi's. Is it true that the norm of any polynomial of these G.U.E matrices tensorize on the right for, by the identity matrix for the Xi's and on the left by the identity matrix for the Yi's? Is it true that any polynomial in these n square by n square matrices, the norm of such any polynomial converges towards the norm of the same polynomial where we replace the G.U.E matrix by semicircular systems. So S, the SIs is a semicircular, a free semicircular system, the TIs also, but we do not assume any relationship between the SIs and the TIs. If R1 is equal to R2, you can choose S to be equal to T if you want. So this is the conjecture, the random matrix conjecture of Ben Ives, as already mentioned by March on his talk on Monday. And with Serban, we proved this conjecture so that thanks to the results of Ben, we know that the Peterson-Thom conjecture is true too. So note that previous work established such strong convergence of matrices, of tensorized G.U.E matrices, but provided the dimension of the matrices on the right-hand side of the tensor product is different from n, let's say m, and provided m satisfies some of these properties. The third one was mentioned by March on Monday. And not also that very recently, Charles Bordenave and Benoît Collins provided an alternative proof to ours of Peterson-Thom conjecture, dealing now with Haar matrices instead of G.U.E matrices. So the rest of my talk will be devoted to the proof of the conjecture of Ben. And first of all, it's obvious that the asymptotic freeness of the Xi's on the one hand, and the asymptotic freeness of the Yi's on the other hand, obviously lead to the convergence of the traces, but the convergence of the norm is not obvious. And the first step in our proof is to reformulate the conjecture of Ben for unitary matrices instead of G.U.E matrices, not R matrices, but unitary matrices. I will explain in a few minutes, and I will explain later why this will be important in our strategy. And this reformulation will be based on the following result of Chang-Yin. This result is the following. Assume that you have a sequence Xn of tuples of elements in some faithful tracial C-star probability space AN to N, which strongly converges towards some tuple X of element in some faithful tracial C-star probability space A to. Remember that strong convergence means the convergence of the traces and the convergence of the norm of any polynomial evaluated in the elements of the tuple and their adjoints. Now, let us consider a rational function R such that the tuple xx star lies in the domain of the rational function R. Then, Cheng-Yin proved that for sufficiently large n, the tuple xn xn star lies also in the domain of R, and moreover, there is convergence of the traces and the norms of the rational function evaluated in the tuple. In roughly speaking, Cheng-Yin extends the strong convergence which involves only polynomials to rational functions whenever it makes sense. And we will use this result of Cheng-Yin by considering the Cayley transform. The Cayley transform is this rational function which maps bijectively the real numbers to the unit circle deprived of 1. Its inverse is given by this rational function. And by elementary functional calculus, one can evaluate psi at any self-adjoint bounded linear operator on some Hilbert space. And this gives rise to unitary operators whose spectrum does not contain 1. So we can define the Cayley transform of any G.U.E matrix xi. So by definition, big Ui is equal to psi of xi. And similarly, we define the Cayley transform, the Cayley transforms, Vi's, of the G.U.E matrices Yi's. And we can also define the Cayley transforms of our semicircular operators, so that little ui is equal to psi of si, and little vi is equal to psi of ti. And to shorten notations, I will denote by big U, little u, big V, little v, the tuples of Cayley transforms. And to shorten notation, I will also denote by a tuple tensor unit identity the tuple obtained after tensorizing by the identity each element of the tuple. And with these notations, Serban and I prove that the norm of any polynomial evaluated in the tensorized Cayley transforms of our G.U.E matrices and the adjoints converges towards the norm of the limiting operators. And since, thanks to this formula of the inverse Cayley transforms, any non-commutative polynomial in tensorized G.U.E matrices is actually a rational function in their tensorized Cayley transforms. Thanks to Yin's result, we can deduce from the strong convergence of Cayley transforms the strong convergence of tensor products of G.U.E matrices we wanted to prove. And so the advantage of dealing with these Cayley transforms of G.U.E matrices instead of dealing with G.U.E matrices is that the UIs and the VIs are unitary matrices, whereas the sequence of G.U.E matrices is not bounded. And I will explain later why this will be important in our strategy. So the rest of my talk will be devoted to the proof of the strong convergence of Cayley transforms. first of all, as previously mentioned, it's obvious to prove the convergence of the traces. And then by using an approximation of the operator norm by LP norms with respect to tau, it's easy to deduce from this convergence of traces this inequality, that is a lim-inf of this norm evaluated, of the polynomial evaluated in these n square by n square matrices, is always greater than the norm of the polynomial evaluated in the limiting operators. So that the difficulty really lies in proving this inequality, that the lim sup is always smaller than the norm of the polynomial in the limiting operators. And to prove such an inequality, we use the so-called linearization trick that was inspired by a paper by G.U.E and developed by Hagerup-Turbersen in 2005 to prove strong asymptotic freeness of independent G.U.E matrices. And roughly speaking, this linearization trick tells you that in order to prove such an inequality, which involves any polynomial P, it is sufficient to prove an inclusion of spectra of any self-adjoint affine polynomial, provided you allow the coefficients to be matrix valued. More precisely, here this linearization trick. Imagine that you have a sequence of random matrices, BIs, big BIs, which is almost surely bounded, and assume that for any fixed integer number m, any fixed m by m matrices, xi, which is self-adjoint, and gamma i's, you are able to prove that for any positive epsilon, almost surely for large n, the spectrum of this affine polynomial in the BIs and the adjoints with matrix valued coefficients, xi, gamma I, and gamma I star. Imagine that you are able to prove that the spectrum of this affine polynomial is included in an epsilon neighborhood of the spectrum of the same affine polynomial, but now evaluated in some operators, little BIs. Then you can state that almost surely for any star non-commutative polynomial Q, we have the lim sup of the norm of Q evaluated in the matrices big BIs is always smaller than the norm of Q evaluated in the little BIs. So since this is exactly such an equality we want to prove, so that we are going to look at a fine polynomial of the involved matrices in our problem, that is the tensorized Cayley transform of the Xi's, that is UI tensor identity, the adjoints, and the tensorized Cayley transforms of the Y's, that is IN tensor J's, and the adjoints. And we fixed an integer m, we fixed m by m matrices, and we consider this affine polynomial with m by m coefficients. This is mn square by mn square matrices, matrix. Let's call it Sn. And similarly, let us define S as this self-adjoint polynomial, the same polynomial, with matrix valued coefficients in blue, but now evaluated in the limiting operators, that is the tensorized Cayley transforms of the semicircular operators. And Serban and I, we proved that indeed for any positive epsilon, almost surely for large n, the spectrum of this mn square by mn square matrix will be included in an epsilon neighborhood of the spectrum of S. And in order to prove such an inclusion of spectra, we use a method that was developed by Hagerup Pedersen and then a bit generalized by Anna Schulz when she dealt with strong asymptotic freeness of G.U.E matrices, independent G.U.E matrices. So the method is the following. Let us consider the self-adjoint affine polynomial Sn. And let us consider the resolvent of Sn at a point z. Let us take the trace and the expectation. Let us call it Gn of z. So this is actually the mean Stieltjes transform of the empirical spectral measure of this mn square by mn square matrix. And similarly, define G of z as being the trace of the resolvent of S at a point z. And with Serban, we prove that up to an error term, which is of order 1 over n to the power 4, and which can be bounded by some polynomial q with non-negative coefficients in 1 over the absolute value of the imaginary part of z. Gn of z is equal to G of z plus some E of z over n square, where E is a Stieltjes transform of some distribution lambda, whose support is included in the spectrum of S, and such lambda of 1 is equal to 0. And then, just sticking to the method of Hagerup, Pedersen, and Schulz, we can deduce from such an inequality the inclusion of the spectrum we wanted to prove. Therefore, let me very briefly remind you the progressive reduction of the problem. We want to prove strong convergence of tensor G.U.E matrices. Thanks to Yin's result, we reformulate this strong convergence in terms of Cayley transforms of G.U.E matrices, which are unitary matrices. Thanks to reionization trick, we saw that it is sufficient to consider a fine polynomial in our matrices with fixed matrix valued coefficients. And we saw that thanks to Hagerup, Pedersen, Schulz approach, it is sufficient to consider expectation of trace of the resolvent of our affine polynomials, Sn and S, and to prove such an inequality. But the method of Hagerup, Pedersen, and Schulz needs this inequality to be true for all z in C minus R. And most papers that put into practice the method of Hagerup, Pedersen, and Schulz used to prove such an inequality by bringing out an equation satisfied by G, an approximate equation satisfied by Gn, and then they deduce such an inequality from these equations. But actually, we failed with such a strategy here, and we decided to use another strategy based on a series expansion of the resolvent of our resolvents. But actually, such a series expansion only holds for large z. But we need such an inequality for all z in C minus R. Therefore, the idea is the following. Instead of proving such an inequality, we are going to prove an equality for large z with explicit formulas for E of z, delta n of z, in such a way that we can state that E and delta n have analytic extension on C minus R, so that we can extend the identity that we proved only for large z to the whole C minus R just by analyticity. So the rest of my talk will be devoted to the proof of such an identity for large z. So, since we deal with unitary matrices, this operator is obviously bounded by this constant here, which only depends on the norm of the fixed m by m matrices, so that for z, whose modulus is greater than this constant, we have this series expansion of the resolvent. So you see here that it is important that the sequence of matrices is bounded, since we will use series expansion for large z greater than some fixed constant. And now we are going to focus on the pink term. So please only look at the pink terms in these slides and do not matter on the rest of the terms, because we want to make an expansion, to develop each term here in such a way that we bring out the terms involving the VI's and the adjoints. So we make such an expansion. So please just focus on the pink term. Do not matter about these terms. What is important is that on the left-hand side, the terms are independent with the VI's. It just involves the fixed matrices, beta i's and xi, and ui's. So it is independent of the VI's, so that when we take the trace and the expectation in order to get Gn of z, so Gn of z is by definition the expectation of the trace of the resolvent, you get that Gn of z is equal to an infinite sum of mixed moments of the VI's and the adjoints multiplied by some term, but please do not matter about this term. Just focus on the pink term. So now the idea is to use a precise expansion in 1 over n of these mixed moments of the VI's and the adjoints. Remember that the VI's are Cayley transforms of the G.U.E matrices yi's. And the first task, donc the idea is to obtain such precise expansion and then to inject them in this infinite series. This infinite sum, sorry. And so the first task consists in establishing such a precise expansion in 1 over n of these mixed moments. And this is essentially done thanks to a wonderful work of Félix Parrot. Félix considered the expectation of the normalized trace of any polynomial in independent normalized G.U.E matrices, and he obtained an expansion in 1 over n, or 1 over n squared, more precisely, of such an expectation with explicit formulas for the coefficients nu(i). And actually, he obtained such an expansion at any order, but we will only use such an expansion up to the order 2. And so the nu(i)'s, the coefficients nu(i)'s and nu(i)'s(m) are explicit with tools from free probability theory. And Felix formulas for the coefficient nu(i)'s involve the following operators acting on polynomials: the free difference quotient, which is this linear map which maps such a monomial to this sum of tensor product of monomials. The flip operator, which is a linear map that just switch both sides of the tensor product. The hash operator, that which is a linear map which just multiply both sides of the tensor product. And finally, the linear map dj, which is just this composition of the previous operators, so that I would like to notice that in all the following, I will denote by x underline by underline r a tuple x1, etc., xr. So if you consider a polynomial p with r indeterminates, j of p will be another polynomial in R indeterminates. So just to give you a flavor of the wonderful formula of Felix, let me present you the precise formula of nu1 of P in the expansion of Felix. So nu1 of P will involve the following operator R1 acting on polynomial in R indeterminates. So you start with P, which is a polynomial in R indeterminates. di of P, as we have just shown, is another polynomial in R indeterminates. Now you apply free difference quotient. This introduces a tensor product. And to each side of the tensor product, you apply this operator, flip, composed with free difference quotient. So each of these operators introduces another tensor product, so that when you start with a polynomial P with R indeterminate, this is something like a finite sum of tensor of the tensor product of four monomials, and we decided to call x1 the indeterminates of the first monomial, x tilde 1 the indeterminates of the second monomial, x tilde 2 the indeterminates of the third one, and finally x2 the R indeterminates of the last one. And the hash operator to the power 3 just multiplies everybody. so that R1 of P, the resulting R1 of P, is just a polynomial now in 4R indeterminates. And here is the precise formula of Felix for nu1 of P. Felix evaluates this R1 of P in particular operators, in particular R tuples of operators that are built from 7 3R semicircular system like this, and 2 parameters T1 and T2. So this are each of this is a R tuple of operators, and then it takes a trace, multiplies by this exponential, and integrate over T1, T2. This is nu1 of P by definition. And similarly, all the coefficients in the expansion of Felix involve some operators Ri's that act on P, on the polynomials. And it turns out that one can write the formulas defining the Ri's in terms of so-called differential operators applied to non-commutative functions. So I refer the interesting people to the book of Kaliusny, Verbowetsky, and Vinnikov for an introduction to non-commutative functions. Serban taught me all I know about non-commutative functions. Thanks, Serban. This will allow us to extend Felix formulas to some rational functions in G.U.E matrices. And let me present you some basic facts about non-commutative functions theory. And first of all, given a C-star algebra B, a non-commutative set over B to power R is a family of sets indexed by n, such that for any n, omega n is some subset of R tuples of matrices with entries in B. Roughly speaking, omega is stable by direct sum, and moreover, omega n is stable under conjugation by complex unitary matrices. Here is an example of a non-commutative set. The set of matrices, of tuples of matrices, whose with entries in B, whose imaginary part is between -1 and 1. And a non-commutative function on such a non-commutative set is a family of functions Fn, such that Fn maps omega n onto matrix n by n matrices with entries in some possibly different C-star algebra B tilde. F, roughly speaking, F commutes with direct sum, and commutes with conjugation by complex invertible matrices. So this is the definition of a non-commutative function. And an example of non-commutative function is given by polynomials, or also our Cayley transform, or this function, which is these are non-commutative functions on the set of matrices whose imaginary part is between -1 and 1. So it turns out that if you evaluate a non-commutative function on upper triangular matrices, the right upper corner of the image is a linear map with respect to the initial upper right corner. And this is called, the delta is called the differential operator. And we can also define the partial differential operator by evaluating this differential operator at this particular tuple, where B is at the place number J. And a rather spectacular fact is that locally bounded non-commutative functions defined on an open non-commutative set are automatically Fréchet analytic, and we can recover the usual Fréchet derivative in that way. And we will use this analyticity of non-commutative functions in our proof. And actually, delta F, the differential operator of F, is a map on sets, a product of omega n, taking values in the space of linear continuous maps from the set of matrices to itself. And this is a particular case of a so-called non-commutative map of order 1. And actually, I won't go into details, but one can define the set Tk of non-commutative functions of order k and define the differential operator on this set, and which they carry with them in upper triangular matrices in a manner similar to that of F that we previously saw. And there is also analyticity under very mild conditions of local boundedness. So I won't go into details of this. But now let us come back to the formula of Felix. And actually, we can identify the free difference quotient with the differential operator. Indeed, remember that the free difference quotient of such a monomial M is the sum of tensor products of monomials. And now let us compute the differential operator of M. By definition, you have to evaluate M on upper triangular matrices, putting some C at the place for the indeterminate J, number J. So let us compute such the monomial evaluated on these upper triangular matrices, and by definition, the differential operator, the partial differential operator of M is this upper right corner. More precisely, it's this linear map given by this upper right corner. So you can see that the free difference quotient can be identified with this linear map, so that we can identify the free difference quotient and the partial differential operator. But actually, we can also identify the operator flip composed with a free difference quotient, which appeared in the formulas of Felix. We can identify it with the differential operator of P, provided you view the polynomial P as being in the opposite algebra. And the hash operator in the formula of Felix just actually consists in the word of non-commutative functions in an evaluation of the linear maps. And the last operator that appears in the formula of Felix is dj, which is just a composition of the previous operations. So actually, remember that the formula of Felix for nu1 of P was given by this integral. And we can, by viewing P as a non-commutative function, we can rewrite this operator R1 in terms of differential operators delta on non-commutative functions, since we have identified each of these operators. Now, let us consider this non-commutative function on this set, this non-commutative set. It makes sense to apply R1 to these non-commutative functions, since we expressed it in terms of differential operators, so that we can extend the formula of Felix in that way on these non-commutative functions. Just by sticking to the definition of Felix, we can define nu1 of this non-commutative function as exactly the same formula, but now R1 is just expressed in terms of differential operators on non-commutative functions. And now we evaluate exactly as Felix did in the same operators, tuples of operators, take the trace and integrate exactly as it did. And thanks to the extension of U1 on non-commutative functions, we can prove, using analyticity properties of non-commutative functions, that the formula of Felix can be extended to Cayley transforms of G.U.E matrices with explicit coefficients for the expansion. So let's come back to our initial problem. Remember that we wrote the expectation of the trace of the resolvent as an infinite sum of mixed moments of the VI's multiplied by some coefficient. We do not mind, just once more focus on the pink term. And now let us, since we obtained such an expansion in 1 over n squared of the mixed moments of the VI's, let us make the replacement in this infinite sum. So when we replace the pink term by its expansion, actually we obtain 3 convergence series. The first one involves the red term here, the second one, the blue one, and the last one, the brown term. now we have to recognize these series, these convergence series. For the first term, it's very easy. I mean, when we replace the pink term by the red term here, it's easy to see that this series corresponds to the series expansion of identity tensor tau of this resolvent, where we replaced the matrices big VI's by the operators, the limiting operators VI's. And for the other two series, I mean, when we replace now the pink term by the blue one or the brown one, the idea is the following. Actually, the idea is to notice that if, let us fix some complex number z. Actually, there exists some epsilon 0, such that if the variable y is in some non-commutative set like this, with a tilde replacing a here, that is matrices whose imaginary part is between minus epsilon 0 and epsilon 0, then it turns out that this function is, this resolvent is a non-commutative function in xi's, so that it makes sense to apply the differential operators involved in the definition of the new i's. And therefore, this, thanks to this remark, we can state that this series is actually the series expansion of this this function, which is the identity tensor nu1 applied to this non-commutative function in the xi's, where nu1 is once more given by the formula of Felix, where R1 here is expressed in terms of differential operators. This makes sense since this is a non-commutative function in the third, in the last variables. And similarly, for the third series, which involves the brown term here, it corresponds to the series expansion of the identity tensor nu2 applied to these non-commutative functions in the xi's. Therefore, we obtain that Gn of z, that is the mean Stieltjes transforms of our mn square by mn square matrix Sn, is the sum of three terms where the matrices VI's disappeared, but where the UI's still appears. So now we just iterate the process, focusing now on the UI's, in order to replace it by the limiting operators. And by iterating the process, we obtain the identity we wanted to prove for large z. And since the E of z and delta n of z are explicit, we are able to state that they have analytic extension on the whole C minus R, so that the identity can be extended to the whole C minus R, and we are done. So thank you very much for your attention.